Hello, let's do section 3.6 today, which is implicit differentiation and related rates. What is implicit differentiation? Implicit differentiation is taking the derivative with respect to x, okay? And it will indicate to you, the problem will indicate to you what your variable is. Anytime you see the variable y, you must take its derivative and write dy dx. Okay. Why do we do this? WHY, no pun intended. The reason for this is because to indicate that we are taking the derivative with respect to x. Okay? So let's do an example of this. Use implicit differentiation to find dy dx when x squared plus y squared equals 25. Okay? This is the equation of a circle. This is a circle centered at 0, 0 with radius 5. Okay? Let me take the derivative of this, explicitly. So let me just pull up another page here. Oops, where's my mouse? Okay. Let me just pull up a third page here. And so it was x squared plus y squared equals 25. If I wanted to take the derivative of this explicitly, which is what we've been doing all along, explicit differentiation, we would solve for y here, so I subtract x squared from both sides, and then take the square root, right? It's y squared. And when you take a square root, it's always plus or minus. The plus is the top half of this circle, and the minus is the bottom half of this circle. So we would have to differentiate these separately. So let me just look at the square root, the positive side, the top half. And this we can write as 25 minus x squared raised to the 1/2. And then if I wanted to take the derivative of this, y prime, 1/2 comes out front. And we get 25 minus x squared raised to the negative 1/2 times the derivative of the inside, which is minus 2x. Okay? And then if I simplify this, the 25 minus x squared raised to the negative 1/2 becomes 25 square root of 25 minus x squared on the bottom. There's a 2 on the bottom, and there's a minus 2x on the top. Okay, so on the minus 2 and the positive 2, so the 2 over 2 gives me 1, and I have a minus x on the top, and then the square root of 25 minus x squared, isn't that just equal to y? So I'm going to call that minus x over y. And that is the derivative. Or you can write it as minus x over square root of 25 minus x squared. What does this tell you? This is the slope of the tangent line at any point. Okay, and then you would have to do the negative part, y equals negative square root of 25 minus x squared, separately. That's explicit differentiation. Let's go back and do the same problem, but implicitly. Okay, so it says anytime you see a variable y, you must take its derivative and write dy dx. So let's do this one. So this is my function. And I want to take the derivative of this. And I always do this. I write d over dx, and I put parentheses around the whole thing. And that reminds me that I have to take the derivative of the left side and the right side. The derivative of x squared is going to be 2x. The derivative of y squared is 2y. But we took the derivative of y with respect to x. So we have to write dy dx. And the derivative of 25 is equal to 0. Now I need to solve for dy dx. So I can get the 2y dy dx. Let me leave it on the left side. And I will subtract 2x from both sides. So I'm left with negative 2x. And then I'm going to divide both sides by 2y. Okay, and then I'm left with dy dx equals minus 2x over 2y. The 2's can go away, right? 2 over 2 is 1, and I'm left with minus x over y, which is what I had when I did this explicitly. Okay, that's the same thing I got here, minus x over y. So when you do this when you do implicit differentiation, excuse me. So when you do implicit differentiation, it's a lot faster, it's simpler. We can deal with complicated functions a lot better. Notice here that what we're trying to do is find dy over dx. So that's what we did. That's what we solved for, dy dx. Okay. This is again the slope of the tangent line. Okay. And it says find the slope of the circle. Excuse me. Find the slope of the circle at 3, 4 and at 3, negative 4. So let me draw a little picture to see what's going on. So this is my circle of radius 5. So this is 5, negative 5, 5, negative 5. At 3, 4. So when x is 3, 1, 2, 3, 4, 5. Okay, when x is 3, there's 2 points here, right? There's a point here, and there's a point here. And it says find the slope. One of these is going to be like this, and one of these is going to be like this, right? And this is the point 3, 4. When you plug 3 into here, you get 4. When you plug 3 into here, you get negative 4. So all we have to do to find the slope is we just have to plug this into dy dx. The slope of the tangent line is equal to dy dx, which is minus x over y. So at 3, 4, the slope is equal to minus 3 over 4, minus x over y. And at 3, negative 4, the slope is equal to minus x, so that's minus 3 over minus 4. All I did was plug x and y into the derivative. And I get positive 3, 4. So this is interesting. Look at this. When your point is 3, 4, which is up here, your slope is negative 3, 4, and this is going down, right? That's our tangent line. When your point is 3, negative 4, which is down here, your slope is going to be positive 3, 4, which is why we have this line. That's the tangent line. Okay. Let's do some more derivatives. So let me write down some examples for you. So the first one is, let's take the derivative x to the 4th. Let me write down all these examples and then and the second example is d over dx y to the 3rd. Okay. Number 3 is d over dx x cubed y to the 5th. And the fourth one, I'll put that here, is d over dx square root of x. Okay. Excuse me. Now it says some explicitly, some implicitly derivatives. So how do we know whether we have to do explicit or implicit differentiation? Well, the first one, there's no y variable here, it's only x. So this we would just do normally like we've been doing all along. Bring the 4 out front, x to the 3rd, and that's it. That's the derivative of x to the 4th. So that was explicit differentiation. Okay. This one, now we're taking the derivative with respect to x but of y. So here I need to do implicit differentiation. What's the derivative of y cubed? 3y squared. But I took the derivative of y with respect to x. Alright, how about this one here? X cubed y to the 5th. Well, it's x and y together, isn't it? So, again, if it was just x, we would do what we've been normally doing. But now we have to do implicit. And here we have two different functions. So we have to use the product rule. Call this f, call this g. Let me write f is equal to x cubed. F prime is equal to 3x squared. G is equal to y to the 5th. And G prime is equal to 5y to the 4th. but don't forget dy dx. We took the derivative of y with respect to x. So now I need to indicate which one. I need to write the product rule. F prime g, remember it's f prime g plus g prime f. Okay, so f prime is 3x squared times g, which is y to the 5th, plus g prime, which is 5y to the 4th, dy dx, times f, which is x cubed. Okay, so I have f prime g plus g prime f, and then we can rewrite it like this. What I have above is fine, but let me just write it like 5. It's standard to put the x first, then the y, and then the dy dx at the end. Okay, these are being multiplied together. Multiplication is commutative, which means it can move back and forth. Okay, so for that one, since we're dealing with both x's and y's, they're being multiplied together, we have to use the product rule. Okay, how about this one, square root of x? Well, that one is, there's no y variable involved. This is just regular explicit differentiation. This is the same as x to the 1/2, which is 1/2. The derivative of that is, now here I just rewrote it. I did not take the derivative. Now I'm taking the derivative, 1/2 x to the negative 1/2, and you can rewrite that as 1/2 root x. Okay. The general rule of thumb is if your question is in radical form or radical notation, then your answer should also be in radical notation. Okay. So here are some steps to finding for doing implicit differentiation. So you're going to be given an equation. You should differentiate both sides with respect to x. Whenever you differentiate y, whenever you take the derivative of the y variable, write dy dx. Collect all terms involving dy dx on one side and all others on the other side. Factor out the dy dx and solve for dy dx by dividing. Let's do an example. Okay. So we have here y to the 4th. So this is my function, and I'm going to just do this. I need to take the derivative of this with respect to x. So there we go. Okay, that tells me the derivative of both sides. The derivative of y to the 4th is 4y cubed. Don't forget the dy dx. Plus, what's the derivative of x cubed? 3x squared. Do I need to write dy dx here? No, because I did not take the derivative of y. I just took the derivative of x. Okay. For this one, I have to use the product rule. So f is 2x squared. G is y squared. So that means f prime is 4x. G prime is 2y dy dx. Don't forget this, guys. Every time you differentiate y, you have to write dy dx. Okay? Plus, excuse me, so that just like we did the product rule up here, we have to do the product rule over here. Excuse me. Okay, so we're going to do f prime, which is 4x, f prime g plus g prime times f. Okay. Now, this is f prime, this is g, here's g prime, and here's f. I just switched them, that's okay. Okay. Now, you ask yourself, why did I not write dy dx over here when I wrote the y squared? Well, I didn't take the derivative of y squared. That's just the original function g. The derivative taking happens here in g prime. So that's why we write the dy dx here and not here, okay? It's only when you take the derivative of y that you write dy dx. Okay? And all of this is equal to 0. The derivative of 7 is 0. Alright, so now I can simplify this. I'll get 4y cubed dy dx plus 3x squared plus 4xy squared plus 2 times 2 gives me 4x squared y dy dx. Okay, and that equals to 0. Now I have to collect everything with a dy dx on one side and everything without a dy dx to the other side, right? That's what my steps tell me. So let me subtract 3x squared and 4xy squared from both sides. Okay. And then on the left side I'm left with 4y cubed dy dx plus 4x squared y dy dx equals, this is minus 3x squared minus 4xy squared. Okay. And then the next step is to factor out the dy dx. So when I pull out a dy dx from the left side here, what am I left with on the inside? Well, there's a 4y cubed left, plus 4x squared y, and then there's a minus 3x squared. I'm running out of space, I'll just write it here. Minus 4x y squared. Okay? Now I have to get the dy dx by itself, so I'm going to divide both sides by this stuff, whatever's inside the parentheses. Okay? So that gives me, I'll just continue here. That gives me dy dx equals, the top I have 4y cubed plus 4x squared y divided by, oh, I'm sorry. Let's look at that again. What do I have on the top? I have this. I have this. Minus 3x squared minus 4xy squared minus 3x squared minus, that's on the left, that's on the right side, and then I'm dividing both sides by this guy here. 4y cubed plus 4x squared y, right? So all this stuff was here, 4y cubed plus 4x squared y, okay? So that is my dy dx. Okay, that is the derivative of this function. It says evaluated at x equals 2 and y equals 1. So at the point when x equals 2, y equals 1, you just have to simply plug in 2 and 1. Oh my goodness, my pen is going. 1 cubed plus 4, 2 squared times 1. What does that give me? 2 squared is 4 times negative 3 is negative 12. Minus 4 times 2 is 8 times 1 is 1, so that's minus 8. That's 4 plus 2 squared is 4 times 4 plus times 4 is 16. Okay. So that gives me minus 20 over positive 20, which is negative 1. Okay. What does this tell you again? Remember, this is the slope of the tangent line. So at that point, 2, 1, of this function, that is the slope of the tangent line, negative 1. Okay. Let's review examples 5 and 6 in your book. So here's example 5 in your book. Okay. They give us the demand equation, and it says use implicit differentiation to find dp dx, evaluated at p equals 10. Okay, so we have to be a little bit careful here because we're not dealing with x's and y's. We're dealing with x's and p's. So think of p as your y variable. Okay. So we have x equals So all I did there was just rewrite rewrite the function. Now, and I want to take the derivative of this with respect to x, right? It says dp over dx. So that means that x is your variable. Okay? Every time we differentiate p, you're going to write dp dx. Same thing as every time we differentiated y, we would write dy dx. Okay, so now we can write this, we can do this as, you know, you write it as x equals 1900 minus p cubed raised to the 1/2. We can do that. But then what that'll do is, I'm going to have to use a chain rule, right? It's going to get a little messy. So what's a good idea is to take, to square both sides. So even before we do this, let's do this. Even before we do this, let's square both sides, right? What you do to one side, you do to the other. So because we have an equation, we're not really changing anything. Okay? So then I'm left with x squared equals 1900 minus p cubed. Okay, that was this. Now it makes the derivative taking a little bit easier because I have the ability to do implicit differentiation. What's the derivative of x squared? 2x. What's the derivative of 1900? 0. What's the derivative of minus p cubed? 3 comes out front, so you get minus 3p squared. Don't forget the dp dx. We took the derivative of p with respect to x. Okay. Now, the 0 can just go away. That's so I'm left with just negative this, and I can solve for dp dx. Divide both sides by negative 3p squared. Okay. So now, that's it. That is dp dx. dp over dx. It says evaluate it at p equals 10. So at p equals 10, but I don't have x, do I? Well, I do, because I know x is equal to 1900 minus p cubed, and the square root of that. So that's the square root of 1900 minus 10 cubed, which is 1000, so that'll be square root of 900, and that is 30. Okay? So when p is 10, x is 30. So dp dx is 2 times 30 divided by negative 310 squared, which is 60 over 10 squared is 100 times negative 3 is negative 300, right? And then you can do this business of crossing out one of the zeros. Basically, I'm dividing top and bottom by 10, so I get 6 over negative 30, which is negative 1/5, and that is negative 0.2. So this is your dp dx. Now what does this tell you? We have to interpret the meaning, right? Let's go back up here. So this is a demand equation, right? P probably stands for price, and X is the number of items. Okay, that's usually standard. And the demand is X is the number of items is based on this based on the price, right? We have X as a function of P, so the number of items sold is dependent on the price. So when P equals 10, when the price is $10, I would assume, at $10, the demand dp dx, so that's the change in price, so that's the change in price divided by the change in the demand, or the number of items. Okay. So negative 0.2 is negative 0.2 over 1. So when your product is priced at $10, for every, so when P goes down by 0.2, which is 20 cents, X goes up by 1. See? This is negative, so that's going down. 1 is positive, so that's going up. So at $10, the rate of change, remember the derivative is rate of change. The rate of change of price is negative 0.2, which means that for each 20-cent decrease, that's negative 0.2, 0.2 or $0.20, which is 20 cents for each 20-cent decrease in price, the demand goes up by 1 unit or 1 item, whatever you're selling or producing. Okay? Alright, let's look at example 6. Okay, example 6 says a pebble is thrown into a pond, causing circular ripples to radiate outward. If the radius of the outer ripple is growing by 2 feet per second, how fast is the area of the circle growing at the moment when the radius is 10 feet? Okay, so we need kind of write, for these kind of problems, I always write down what's given and what do we need to find. Okay, that helps keep it straight. So given is, they tell us the radius of the outer ripple is growing by 2 feet per second. So that's the rate of change of the radius. So 2 feet per second, right? That's dr dt. That's 2. And then the units will tell you where things go. R is measured in feet. T is measured in seconds. So it's feet over seconds, dr over dt. Okay? And it says how fast is the area of the circle growing? So we need to find the rate of change of the area. So that's dA dt. Okay? How fast means how fast is the area changing with respect to time when the radius is 2 feet, so when r is 10. Okay. Now for these kind of problems, you're always going to have equation you're going to use or some formula. Here we're looking at the radius of a circle and we're finding the area. So the equation we're going to use is the area of a circle, which is pi r squared. Okay. This we need to take the derivative of with respect to time, d over dt. So then we do dA over dt equals, now pi is a constant, so leave the pi alone. The 2 comes out front. Okay, r is our variable, and minus 1. So the 2 comes out front, so we get 2 pi r, and then we took the derivative of r with respect to t. So you have to write dr dt. Oops, what's up with my pen today? Alright. So now we can just plug in what we need. dA dt is what we need to find. 2 pi is, just write it as pi, r is 10, and dr dt is also 2. So it's 2 times 2, which is 4 times 10, which is 40 pi. Okay, and that's the exact answer. Okay, so the area is changing at a rate of 40 pi. What are my units? Well, the units for area are feet squared, and then it's dA dt, which is feet squared per second. So that is the rate of change of the area at when the radius is 10 feet. Okay, and then just so we can understand this number conceptually, we can type this in, 40 pi, and get 125.66 or 125.7. So this is the decimal approximation. So that means the area is growing by 125, roughly 126 feet per second from this, for the stone being tossed in. Okay, so let's go back to the notes. That is example 6. Okay, so what we just did, example 6, this was called a related rates problem. Okay, related rates, that was example 6. So first figure out, determine the quantities that are changing with time. So I always what are you trying to find and what are you given? Write those out. Okay, find an equation that relates these quantities. Here we use the area equation. take the derivative of both sides implicitly with respect to t, time, okay? Substitute into the new equation any given value, so then you just plug in your values, and then you solve for what you're trying to solve for, dA, dt, dy, dt, whatever you're solving for. Okay? Let's look at this example here. So a boatyard's total profit from selling X outboard motors is given by this function. Outboards are selling at a rate of 20 per week. How fast is the profit changing when 400 motors have been sold? Alright, so what are we given? Alright, we're given, and what do we need to find? And the equation. Well, let's write down the equation. They give us, some more space here. They give us the profit function, which is minus x squared plus 1000x minus 2000. Okay. What are we given? If outboards are selling at a rate of 20 per week, and x is the number of outboards sold, so they're giving us dx dt, right? They're giving us the rate. So a rate is always dx or d something over dt, 20 per week. Again, look at your units, 20 motors per week. So motors is x, week is t, so that's dx dt. How fast is the profit changing when 400 motors have been sold? So that's another piece they're giving us. X is 400. Okay, 400 motors. And how fast is the profit changing? That's dp over dt. Okay. So what we need to do is take the derivative of this guy, of our major equation, with respect to t. Okay. So then I get dp dt is equal to minus 2x dx dt plus 1000 dx dt. Now notice here, and then minus 0. Every time I take a derivative of a variable that's not t, so see, I'm taking the derivative with respect to t. So anytime you take the derivative of anything that's not t, you have to write d blank over dt. So here I took the derivative of p, that's 1 dp dt, I did not write the 1, minus 2x dx dt, 1000 dx dt. Okay. Now I can just plug and chug, right? Minus 2 times 400 dx dt is 20 plus 1000, and then what is dx dt? 20. So what does that give me? 2 times 2 is 4, times 4 is 16, and then 1, 2, 3 zeros, plus 2, 1, 2, 3, 4 zeros. So that's minus 16,000 plus 20,000, which is 4,000. And what is this? Dollars. Dollars per week. So that is the rate of change, or the rate of change of the profit. So the profit is growing at a rate of $4,000 per week. Okay. Let's look at this example. A study of urban pollution predicts that sulfur oxide emissions in a city will be this S function, where X is the population in thousands. The population of the city 2 years from now is expected to be X equals this many thousand people. Find how rapidly the sulfur oxide pollution will be increasing 4 years from now. Okay, so and then we're not given too much stuff. Let's write down, what do we need to find? Find how rapidly the sulfur oxide pollution will be increasing 4 years from now. Okay, so we are given some things. We're given t is equal to 4, and we need to find how fast the pollution is growing, and pollution is denoted here by capital S, so that's ds dt. And the equation we're going to use is capital S equals 2 plus 20x plus 0.1x squared. and I need to take the derivative with respect to t. Okay, so then I get capital ds dt equals, the derivative of 2 is 0, the derivative of 20x is 20 dx dt, plus this 2 can come out front, multiplied by 0.1 is 0.2x dx dt. Okay. Now, I don't have dx dt. They did not give that to me, and they did not give me x. But what they did give me is the formula for x, so I can find all of this stuff, right? X is equal to 800 plus 20 root t. And t is equal to 4, so I just have to plug in 4. So square root of 4 is 2 times 20 is 40, so that's 840. And then I need to find dx dt. So dx dt, let me take the derivative of this guy here. So dx dt, so this is written as 800 plus 20t to the 1/2. The derivative of 800 is 0. The 1/2 can come out front, so that's 10t to the negative 1/2. And then I don't need to write dt dt. That dt over dt is just 1. Okay. So this becomes 10 over square root of t. Okay. And then when t is 4, at t equals 4, you get dx dt equals 10 over square root of 4, which is 10 over 2, which is 5. Okay. So now I can just plug everything in. So now I get 20, dx dt is 5.2, x is 840, let me circle these, you need these values to plug in. And then again, dx dt is 5. So what does that give me? 100 plus 0.2 times 5 is 1 times 840, which is 840. So I get total 940. Okay. So what is my units here? Find how rapidly the sulfur oxide pollution will be increasing. And that's in tons, and x is in years. So it's 940 tons per year. Okay, so 4 years from now, that's what this is saying, 4 years from now, the pollution will be increasing. 4 years from now, pollution of this chemical, sulfur oxide, pollution will be increasing at a rate. Pollution will be increasing at a rate of 940 tons a year. It's kind of scary. That's a lot of tons of pollution. Okay. So again, this is a rate of change. Okay, it's not telling you it will be 940 tons. It's telling you it will increase by 940 tons a year. All right. So that is all of section 3.6, and this is actually the end of chapter 3. If you have any questions, please feel free to get in touch with me. In the meantime, work on the homework, and thank you for watching.